Alright, let's go. Number 10. The muon descent. In 1937, Carl Anderson and Seth Nettermeyer at Caltech were cataloging tracks in a cloud chamber, trying to identify a strange particle that kept appearing in cosmic ray data. They weren't looking for evidence that time runs at different speeds. They were doing bookkeeping. The particle they found, later named the muon, decays fast. Its measured half-life in laboratory conditions is 2.2 microseconds. Even moving at the speed of light, a muon should travel only about 660 meters before falling apart. Cosmic ray muons are created about 15 kilometers up in the atmosphere. The math is not close. They should never reach the ground. Billions do. Every second. Right now. In 1941, Bruno Rossi and David Hall published their Mount Washington experiment in Physical Review, comparing muon flux at 6,300 feet with muon flux at sea level. Classical decay predicted almost nothing should survive the descent. What arrived was roughly 9 times more than the calculation permitted. The muons were living longer than physics said they could. Maybe muons were being freshly generated at low altitudes. Air shower reconstructions showed they weren't. Maybe the lab measurement of their half-life was wrong. Hundreds of independent measurements since have agreed to within a few nanoseconds. Maybe some unknown interaction preserved them. No candidate interaction survived peer review. The only explanation left standing was the one Einstein had already written down in 1905, moving clocks tick more slowly. The muon's internal clock is running about 9 times slower than ours, because from their perspective, they were barely alive at all. The rain has never stopped. As you read this, muons are passing through your ribcage at 94% of light speed, existing on a schedule that disagrees with the one your body uses. If a particle's clock can slow down enough to save it from death, what makes yours the honest one? Above your head is dramatic. Your pocket is worse. Number 9. The GPS correction problem. In the late 1970s, the U.S. Air Force was building a satellite navigation system. The engineers weren't interested in relativity. They wanted accurate positioning for missile guidance. The system's premise was simple, synchronized clocks on satellites broadcast their exact time. Your receiver on the ground calculates distance from the time delay. This only works if the clocks stay synchronized. They don't. Not naturally. Every day, without correction, the satellite clocks pull ahead of ground clocks, and the entire system fails. The pre-launch analysis, formalized by Neil Ashby of the University of Colorado in his 2003 paper in Living Reviews in Relativity, calculated the drift precisely. Satellites orbit at roughly 20,200 kilometers altitude, moving at about 3.87 kilometers per second. Special relativity slows their clocks by about 7 microseconds per day due to velocity. General relativity speeds them up by about 45 microseconds per day due to weaker gravity. The net is plus 38 microseconds per day, faster than clocks on the ground. Engineers initially proposed ignoring the correction, calling it a physics curiosity. The first operational generation satellite, ENS-2, launched in 1977, carried a switch that could turn the relativistic correction on or off. Without correction, position errors accumulated at roughly 11 kilometers per day. Within 3 days, the network was useless as a positioning system. The engineers who had thought Einstein was overrated turned the switch on and left it on. Every device that has used GPS since has left it on. The device in your pocket is doing this right now. Every location fix it delivers is a calculation that formally acknowledges, as a matter of engineering necessity, not theory, that clocks in space and clocks on the ground do not agree about the passage of time. If the disagreement between clocks is small enough to fit inside a phone, why do you still trust yours as the standard? Even that comparison assumes distance. The next one doesn't. Number 8. The millimeter divergence. Around 2020, a team at GILA in Boulder, a joint institute of NIST and the University of Colorado, led by Jun Ye, wasn't studying aging. They were trying to build a more precise optical atomic clock, useful for redefining the second. General relativity predicts that a clock closer to a gravitational mass ticks slower than one further away. The effect has been measured across altitudes of many meters for decades. The question was, how small a height difference can you resolve? 0.5 millimeter. In their 2022 paper in Nature, titled Resolving the Gravitational Redshift Within a Millimeter Atomic Sample, the Gila group, with Tobias Bothwell as lead author, reported a measurable difference in tick rate between the top and bottom of a single cloud of strontium atoms just about 1 millimeter tall. The clock at the top ran faster than the clock at the bottom by about 1 part in 10 to the 19th power, exactly as Einstein's equations demand. Reviewers checked for temperature gradients in the strontium sample. None were sufficient. They checked for magnetic field variation across the millimeter. Too small. They checked for laser frequency instability. Below the effect. They checked for statistical noise. The signal survived every filter. What was left was the raw prediction of general relativity applied at a scale most physicists had previously assumed the effect would be too small to detect. It wasn't. It was already there. You are taller than 1 millimeter. The top of your skull is measurably in a weaker gravitational potential than the soles of your feet. Your head is aging faster than your feet. Not metaphorically, continuously, for as long as you have stood upright. If your own body cannot agree on what time it is, what were you referring to when you said now? Your body disagrees with itself. Your birthplace disagrees with someone else's. Number 7. The latitude offset. In the 1970s, Neil Ashby, the same physicist who would later formalize the GPS correction, was working through the relativistic geometry of Earth as a spinning oblate body, not a philosophical exercise. Practical geodesy. How to define a consistent global time standard across the surface of a non-spherical, rotating planet. Two effects compete on Earth's surface. First, the planet spins faster at the equator, at roughly 465 meters per second, than at the poles, where surface rotation approaches zero. Special relativity says the equatorial clock should therefore tick slower. Second, Earth's equator bulges. You sit about 21 kilometers further from Earth's center at the equator than at the pole. General relativity says that greater distance from a mass means faster ticking. The two effects nearly cancel. Nearly, not exactly. Ashby's analysis, expanded in his 2002 Physics Today article Relativity in the Global Positioning System, and refined in the international definition of terrestrial time by the International Astronomical Union, established that Earth's surface constitutes what is called a rotating geoid, a surface where the two effects are arranged by geology to almost balance. The residual difference between a clock at sea level near the equator and a clock at sea level near the pole is on the order of parts in 10 to the 12th, small but non-zero, and formally accounted for in modern timekeeping. You cannot escape the effect by moving north. You cannot escape it by moving south. You cannot escape it by moving to sea level. The bulge is not going anywhere. The spin is not slowing measurably in a human lifetime. The tiny clock in your body, cell divisions, neurotransmitter cycles, the pace of an eyelash growing, was calibrated by an accident of birthplace geography. Someone born at the equator and someone born at a pole are aging on faintly, formally different schedules. How different from your neighbor would you have to be born to notice? An offset that small takes a lifetime to see. Two twins made it visible. Number 6. The Kelly divergence. NASA had been running biomedical studies on astronauts for decades. What they lacked was a genetic control. When Scott Kelly was assigned in 2012 to a 1-year IS mission, and his identical twin brother Mark Kelly, a retired astronaut himself, agreed to serve as the ground-based comparison, the agency built a study that had never been possible before. General and special relativity together predict that a person orbiting Earth at IS altitude and velocity will experience less elapsed proper time than a person on the ground. The predicted difference for a 340-day mission is small, roughly 5 milliseconds. The prediction held. Scott returned to Earth a measurable fraction of a second younger than his identical twin. The results were published in April 2019 in Science, in a paper titled The NASA Twin Study, a multi-dimensional analysis of a year-long human spaceflight, led by Francine Garrett-Bakelman of the University of Virginia and Weill Cornell Medicine. The timing calculation cross-checked against the ISS orbital record, an altitude of about 408 kilometers and orbital velocity of 66 kilometers per second, gave a proper time deficit of approximately 5 milliseconds for Scott relative to Mark over the mission. Skeptics asked whether the effect might be an artifact of measurement precision. It wasn't. ISS orbital parameters are known to meter-scale accuracy, and the timing equations of general relativity have been experimentally confirmed to better than 1 part in 10 to the 14th. Others asked whether biological differences complicated the picture. They did. Scott's telomeres lengthened, his gene expression shifted, but none of that erased the underlying temporal fact. 2 people with identical DNA, born minutes apart, ended a single year at measurably different ages. Not by feeling, by calculation, by record. If time can drift apart between 2 people who started identical, what has yours been doing while you weren't watching? Twins made the effect visible, but the arithmetic that predicts them contains a twist most viewers miss. Number 5. The orbital inversion. In the years after GPS went operational, physics educators noticed a persistent confusion in popular explanations. Space equals younger. Astronauts age slower. It was a clean story. It was also, in one important case, wrong. There are 2 clocks in orbit. The first is the ISS, 408 kilometers up, moving at 7.66 kilometers per second. The second is a GPS satellite, 20,200 kilometers up, moving at 3.87 kilometers per second. The naive story says both should age slower. The actual math says one ages slower and one ages faster. They diverge in opposite directions. Clifford Will of the University of Florida, in his 2014 review, The Confrontation Between General Relativity and Experiment, published in Living Reviews in Relativity, laid out the exact figures. For the ISS, velocity dilation dominates gravitational dilation, producing a net proper time deficit of about 25 microseconds per day. Astronauts return younger. For GPS satellites, at nearly 50 times the ISS altitude, gravitational dilation dominates, producing a net proper time surplus of about 38 microseconds per day. Satellites return older. There is no altitude at which space behaves as one consistent effect. There is no simplifying assumption that recovers the popular version of the story. Physicists have looked for one for a century. The equations do not permit it. The orbit determines the direction. The velocity and the height compete, and above a specific crossover altitude, roughly 3,200 kilometers above Earth's surface. The direction of the effect flips. The universe does not care about your intuitions about space. 2 things in orbit around the same planet, obeying the same laws, are aging in different directions relative to you at this moment. If space doesn't tell you whether time slows or speeds up, what does? The equations don't give one answer, because there isn't one. Number 4. The simultaneity collapse. Einstein was 26, working as a patent examiner in Bern, reviewing applications for electromechanical devices, many of them involving the synchronization of clocks across railway networks. He wasn't trying to overturn Newton. He was trying to define what it means for 2 clocks in different places to say now at the same moment. Newtonian physics assumes an absolute universal present. 2 events in different locations either happen simultaneously or they do not, and everyone in the universe must agree on which. Einstein's 1905 paper on the electrodynamics of moving bodies, published in Annalen der Physik, proved that they do not. The result is called the relativity of simultaneity. 2 observers in relative motion, using their own perfectly accurate clocks and their own perfectly correct methods for defining simultaneous events, will genuinely disagree about the time ordering of 2 spatially separated events. Neither is wrong. There is no third observer whose frame is privileged. No experiment can be designed to resolve which one is correct, because the question itself does not have a frame-independent answer. Physicists spent decades trying to identify a preferred frame. The Michelson-Morley experiment in 1887 had already ruled out the ether. Attempts to identify a universal rest frame using the cosmic microwave background give a local reference for cosmology, but not for the underlying physics. The equations remain frame-independent. Every attempt to smuggle absolute simultaneity back into modern physics has failed, quietly, without ceremony. There is no universal now. When you say right now, somewhere in the world, someone is being born, you are speaking a sentence that has no formal truth value across frames. There is no shared instant. Now is a local convenience of the frame you happen to be sitting in. If no experiment can identify a universal present, in what sense does one exist? A statement that abstract only lands when you drop it onto a real sidewalk. Number 3. The Andromeda Sidewalk. Roger Penrose, later a Nobel laureate, was writing his 1989 book The Emperor's New Mind, aimed at general readers. He needed an illustration that would make the relativity of simultaneity feel concrete, not for physicists, but for people who had never considered that now might be optional. Take two people on a sidewalk in an ordinary city. They pass each other at an ordinary walking speed. One is walking away from the Andromeda Galaxy, the other is walking toward it. Ask each of them, at this instant, what is happening in Andromeda, roughly 2.5 million light-years away. They disagree by days. The calculation is straightforward. Andromeda is roughly 2.5 million light-years distant. The relative velocity between two pedestrians walking past each other is on the order of 2 meters per second. Working through the Lorentz transformation for events at that distance, the two pedestrians' hypersurfaces of simultaneity in Andromeda are separated by several days of Andromedan time. Penrose used the vivid example of a hypothetical fleet launching from Andromeda. For one pedestrian, the fleet is already set out. For the other, the decision to launch has not yet been made. The result cannot be dismissed as an artifact of communication delay, that would be the light travel time argument, and it is not what is being calculated. It cannot be dismissed as a paradox of measurement. The two observers are not making a measurement. They are calculating what their frame formally assigns to the present. It cannot be dismissed as a thought experiment about spaceships. The whole point is that the speeds involved are ordinary human walking speeds. Every time you pass someone on the street, the now you assign to any sufficiently distant location diverges from theirs, not measurably by any human instrument. Formally, structurally, if two people walking past each other cannot agree on the present of a galaxy, in what sense are you and the person beside you in the same one? Pedestrians disagree by days about galaxies. Particles do worse over a ring in Switzerland. Number 2. The Proton Slowdown. The Large Hadron Collider at CERN along the French-Swiss border was designed to explore high-energy physics, the Higgs boson, supersymmetry, the substructure of matter. Its designers weren't advertising it as a time dilation experiment. That was simply an unavoidable side effect of the operation. Protons accelerated in the LHC's 27-kilometer ring are pushed to energies of about 6.5 tera-electron volts per beam during nominal high-energy operation. At those energies, their velocity is approximately 0.9999990 times the speed of light. Special relativity gives a Lorentz factor, the ratio of external time to internal proper time, of about 6,930. A single second on a proton's own clock takes roughly 2 hours to complete in the lab frame. The LHC beam parameters were published by the CERN Accelerator Complex in the 2008 LHC Design Report, edited by Oliver Burning and colleagues, in 3 volumes running to nearly 2,000 pages of engineering detail. The calculation is not disputed. It is used every day to schedule beam dumps, calculate collision rates, and interpret decay products. Unstable particles produced in collisions live measurably longer in the lab frame than they should, by exactly the factor the equations predict. Engineers cannot design around the effect. It is not a bug in the machine. It is not a rounding error in the software. It cannot be reduced by better shielding, colder magnets, or more precise focusing. Every attempt over the decades to identify an anomaly in the time dilation prediction at cosmic ray energies, at accelerator energies, at storage ring energies, has confirmed it to within measurement precision, currently 1 part in 10 to the 12th. 100 meters below the surface of the Earth, in a tunnel outside Geneva. There are objects whose internal time is running 7,000 times slower than yours. Their second and your second are not the same object. If their second is 7,000 of yours, whose second was the original? All of it stacks. Now put it on you. Number 1. The shared present that never was. The realization came to physicists slowly, not through a single paper, but through the accumulated weight of every result before this one. It was not proposed. It was noticed. A single human being standing still on a sidewalk, in an ordinary city, at an ordinary latitude, at ordinary sea level, at an ordinary time of day. Not moving, not accelerating, doing nothing. There is no consistent moment inside them. Combine every effect on this list. The muons passing through your body are on a schedule 9 times slower than yours. Your head, under the Gila result extended to body scale height gradients, is aging faster than your feet by about 1 part in 10 to the 16th per metre. A real continuous divergence. Your birthplace, per Neil Ashby's geodesy, gave you a starting offset relative to someone born in another hemisphere. Your relative motion to the person beside you, per Roger Penrose's illustration, means the two of you slice now at distant galaxies differently by days. The GPS satellites overhead, per Clifford Will's review, are running 38 microseconds per day ahead of your wrist. Every one of these is measured, published, and reproducible. There is no rest frame in which all of this collapses to a single tick. There is no shared clock waiting to be discovered. There is no correction factor that patches it. The equations do not admit one. A century of experiment has not produced one. Physicists stopped looking not because they gave up, but because they understood what they were looking for did not exist. You have never, in the entire course of your life, been on the same clock as the person standing beside you. Not once. Not for a single second. The idea that you have was never physics. It was a convenience of being small and slow and not looking closely enough. If everyone you have ever loved has been on a different clock the entire time, in what sense did you meet them at all? The universe is not confused. What is confused is the story you tell yourself when you look at a clock on a wall and imagine your second and everyone else's second are the same object. They are not. They never were. Every anomaly on this list sits at the center of our most tested theory, not at its edge. The disagreement is not a glitch in the machinery. It is the machinery. If you want to see more videos like this, click the video on screen now.